Hello viewers of mine, this is another What the Physics video. This one is, well, we're finishing up basic motion here. We're trying to summarize what we learned about velocity and speed, and then average and instantaneous velocity and speed. And then we're going to move on to acceleration. But let's quickly summarize velocity versus speed. A reminder that velocity is a vector and speed is a scalar. I'm sure you'll find a way to remember the difference between those two. Anyhow, that means velocity is going to be displacement divided by time. Speed is going to be distance divided by time. So the direction in which the object is moving is going to be important, also in case there's any backtracking and such. Okay, but they both have the same unit, meters per second. Okay, and then we talked about average versus instantaneous. Average is if you are talking about your displacement or distance, whichever one you're going for the whole time period, and then you divide that by, divide the displacement or distance by the entire time, you are going to get the average. Okay, doesn't matter if we're going really fast at certain points or going really slowly at other points. It's it's a big spread. For instantaneous, it is talking about how fast you're going at a particular moment. So not over 5 hours of travel or 1 hour of travel, even half an hour of travel. It's when you shrink it down to just a split second worth of distance or displacement, how fast you're going. And that is going to be your instantaneous speed or instantaneous velocity, whichever one you're looking for. Okay, and of course we had our Velociraptor here, and the Velociraptor is not actually going to be Distanceraptor divided by Timeraptor. It's going to be Displaceraptor divided by Timeraptor. Duh, of course everyone knows that. Physics. Okay, let's moving on. Now that we've done our summary, let's move on to acceleration. And we have our learning target. I can calculate acceleration from velocity and time, and I can express and interpret graphical representations of motion maps. We'll do that at the very end. So acceleration, if we are just talking about driving a car, right? So if we are talking about acceleration, we know that when we're driving a car, we're not typically going at the same speed or even the same velocity all the time, right? We're at a stop sign and then we're not moving and then we go faster, right? Or we're coming up on a stop sign and we're slowing down and so on, right? So that's what we're talking about with acceleration. Acceleration is when we are changing our velocity. Now remember, velocity is going to be how fast we're going as well as direction. So it's not just when we're going faster or slower, but it's also when we are changing direction. That's when we're doing acceleration. So acceleration can be speeding up. Acceleration can also be slowing down. So that's kind of different from what we might be used to. A lot of people use the term deceleration. We're not actually going to be using that term, and I'll explain why on the next slide. Okay, so acceleration is when we are changing our speed or velocity in a certain amount of time. And that means our equation, delta V, change in velocity, divided by delta T. And the units for that are going to be the units for velocity, or meters per second, and then divided by the units for time, which are going to be seconds. So we can either have those in terms of meters per second or meters per second squared. You say, how does that work out? Okay, well, meters per second kind of works out like this over here. Meters over seconds times 1 over seconds equals meters per second squared. Now, a lot of times that really just baffles people. So let me write it out again. Okay, so we've got meters per second divided by seconds. That turns into meters per second times 1 over seconds. You say, how does that, I don't get that. Well, think of it this way, just basic math over here. We've got 8 divided by 2 is equal to 4. I'm pretty sure we can all handle the mathematics there, right? Okay, we've got 8 divided by 2 is equal to 4. Oops. Well, when we divide by something, we can also say that's the same thing as multiplying by its inverse. So the inverse of 2 is going to be 1 over 2, right? So 8 times 1 over 2 is also equal to 4. You say, okay, fine. So that means meters per second here divided by seconds down here is the same thing as saying meters per second times 1 over second, the inverse of seconds, and that's how we get meters per second squared. Some people get confused and they say, oh, should the seconds cancel out here? Well, no, as you can see in this case, they should not cancel out. But when we see it like this, I say, oh, no, seconds cancel. They do not. Absolutely, the seconds do not cancel out. You say, well, fair, will seconds ever cancel out for us? Yes, but not when we're dividing meters per second by seconds. Actually, when we're multiplying meters per second times seconds, we'll actually get the seconds to cancel out here. So let's go ahead and see. I got seconds downstairs canceling out with seconds upstairs. If we want, we can put that over 1 to help us visualize. And that just gives us meters. You say, oh, that's interesting. I wonder what that's going to relate to. Wait a minute. It's this equation. I've seen this equation before. It's delta V times T, or delta T, is equal to displacement. That was an equation we used in the previous section. Woo! So we'll actually be looking into that a lot more when we're talking about graphs. But I figured it'd be a nice little introduction right here. So, cool. But that's how the units work out. So let's go ahead and move on. Make sure we get this equation thing down. Which, by the way, we can also help ourselves with this equation here. We saw one of these triangles earlier on. We said if I want to solve for one of these variables, I can just cover it up and then use the dividing or multiplying that the rest of this gives us. So for example, if I want to solve for acceleration, which is here, I can just cover up the a, then it's going to be v over t. Technically, that's the change in velocity divided by change in time, but yeah, it works. If I want to solve for velocity, I'm going to cover that up. I get acceleration times time. Really, that's change in velocity. And then finally, if I want to solve for time, I cover time up. I get delta v over acceleration. Okay, delicious. Delicious. Okay, so let's talk about that whole acceleration is not the same as deceleration, whatever. So acceleration is a vector. Vector, remember, the big deal with that is direction is of huge importance. There's scalars where we don't care about direction, and then there's vectors where we do care about direction. Both vectors and scalars care about magnitude. Magnitude is a fancy way of saying how much, right? But only vectors care about direction. And a lot of the times we talk about direction in terms of north, south, east, west, up, down, left, right, forward, backwards, whatever. We can also express it a little more simply with a negative sign. So if we're saying that if we go in the positive direction, that's forward, and negative direction is backwards, right? That type of thing. Okay. So we got to make sure that we understand what we're talking about here. That positive is in the terms of direction is not the same thing as positive in terms of amount. So let's actually go back to here and we scroll down. Okay, so what I wrote out here is in math class, we're very used to speaking in terms of numbers as like a number line, right? If we've got a positive number is going to be larger than a negative number. That's just how it is, right? If we look at our bank account and Amy has positive or just plain $20 in the bank, right? And Bobby has positive $2 in the bank, or just $2. Obviously, Amy has more money than Bobby. Okay, cool. If my bank statement says negative $25, womp womp, I'm a teacher, I know, yikes. Okay, but if it says negative $25, then obviously Amy has more money than I do, because not only does she have $20 in the bank, I owe money, right? So it's like I have $45 less than Amy. That's just kind of standard what we understand in terms of a number line, right? But in physics is going to be different, because we're not talking about the number line here. We're talking in terms of positive direction and negative direction. So when we say a car is driving in the positive direction, let's say that's just north, right? If I'm talking about driving on Route 28, which is the Centerville Road, right by the movie theater and such. So Route 28, it just goes north and south, right? So we'll say north is going positive. In our case, that's going up toward Herndon and Sterling. And south is going to be the negative direction. And we'll say that's going toward Manassas. If we're saying that I'm going positive 20 meters per second, or miles per hour, it doesn't really matter, but 20 meters per second, and someone else is going south 25 meters per second, we're going to treat that as negative, right? You say, yeah, sure, okay, fine. So positive 20 versus negative 25, what I'm getting at is the person going at negative 25 meters per second, we can all agree is going faster than the person going at positive 20 meters per second. So if I'm going south at 25 meters per second, Amy is going north at 20 meters per second, I can express that with positive and negatives. It is obvious, it should be clear that I am going faster relative to the ground than Amy is, even though I could express mine with a negative sign. But my speed is definitely greater than hers. Okay? Another important thing here is when we're talking about using velocity and acceleration with the positive or negative. So let's say here is a car. Okay? We're traveling north, so that's the positive direction. If I am traveling north, I have a positive direction here, and I'm also accelerating north, so I've got my velocity in green and my acceleration in red. That means I'm going to be going faster. Go faster. I don't know why it's highlighting everything. That's kind of annoying. Okay, that went away. All right, so that rightmost one, the upper right one, is saying it's going faster because my velocity and my acceleration are in the same direction. You say, yeah, I guess it's, but I'd say it's because acceleration is positive there, right? And acceleration over here is negative, so I'm going slower. Okay, when I'm moving in the when I'm moving in the positive direction, my positive velocity, and oh my goodness, all this pop-ups there, and my acceleration is backwards, it's in the negative direction, I'm going to be slowing down. I'm applying the brakes. And then in this case, kind of in the middle, or I've got a positive velocity and acceleration is 0, that's going to be a nice constant velocity. Constant velocity. You say, yeah, okay, that's fine. That's exactly what I would be expecting. However, when I start traveling in the negative direction, that's kind of what throws people off. Because a lot of people would say, oh yeah, you know, when I'm this here, this I had a positive acceleration, and this one over here, I was decelerating. I don't want to use the term decelerating because I don't want people to think decelerating is the same thing as negative acceleration. Because let's look at these again. In these cases right here, I am going in the negative direction, right? I'm heading toward Manassas. I'm going south. We're treating south as negative. So in this case, my velocity and my acceleration are both negative. I'm going in the negative direction. They're both velocity and acceleration are in the same direction, so I'm going to be going, oops, so it doesn't disappear. I'm going faster. I'm speeding up there. And then here I am in the middle. Once again, with the acceleration is 0, so that's going to be a constant velocity. And then in the bottom right one, where I have a negative velocity, but I have a positive acceleration, I'm actually going to be slowing down. I'm slowing down here. Even though my acceleration is positive, because my acceleration is in the opposite direction of the velocity, They're like, imagine like they're fighting against each other. That means I have a negative velocity, positive acceleration. I'm going to be slowing down. You say, that is something weird. It's kind of weird to think of. So, in other words, I'm not going to be using the term deceleration because that is just too much of a loaded term. Okay? All right, so you can have, I'd say it's easiest to think in terms of, am I speeding up or slowing down? Am I going faster or slower? Good stuff. All right, so in here it says we have these cars, and the cars are in the top line are going in the positive direction, and I'm supposed to be drawing out the vectors here. So if I'm speeding up, if I'm moving this way, this is my velocity, my acceleration is also going to be in that direction. I'm not going to change the colors in here. It's a little more difficult to change colors in a slide deck mode. In the top right mode, or top right situation, I'm still moving in the positive direction. So, my velocity is to the right. I don't know what's up with that line. And the acceleration is going to be negative, so it's like this. So I'm going to be slowing down, slowing. How about when I'm traveling in the negative direction, when I'm going south, right? South along 28 toward Manassas, right? So my velocity is here for both cases. Both cases, my velocity is to the left. I don't know what's up with those random horizontal lines. Anyhow, velocity is to the left. If I am speeding up, if I'm going faster, my acceleration is going to be in the same direction as my velocity. If I'm slowing, my acceleration will be in the direction opposite of the velocity. Hopefully that's making sense. Yeah. All right, let's move on. Let's talk about applications for acceleration. So I always try to incorporate applications, real world applications, and a lot of times I'll do driving because you're new drivers, or you're going to be new drivers, and driving is exciting for you. Also, I try to do some sports, and I try to work those in. So I am not much of a runner, but I've talked to people before, and that are sprinters and such, and I say, oh, so I guess when you're sprinting, you just try to go as fast as possible for as long as possible, right? That is not actually the case. When you are sprinting, if you just start off, or actually when you're doing any type of running, if you just start going like to the wall, or walls out, you're just going crazy fast, you are going to start off really well, but then you're going to run out of gas pretty quickly. So turns out that your coaches should be saying, and I'm sure any experienced runners will know this, that you want to actually increase kind of gradually over time. This is Usain Bolt. Perhaps you've heard of Usain Bolt. Pretty darn fast, right? Pretty famous for breaking world records, in fact. So this is Usain Bolt's time splits for a 100-meter dash. And I went ahead and ran the average velocities throughout here. And it turns out for the first 10 meters, he was going on average about 5.41 meters per second. And then for the next 10 meters, it's went at 9.8 meters per second, then 11, 11.5, speeding up. And then about 2/3 of the way done, he's maxing out at 12.2 meters per second. And then actually starts, when he's just almost out of energy, he does start slowing down because he used up so much energy early on. But these are the splits for when he is running, and as you can see, he's using physics, whether he's realizing the physics or not. He's using physics in terms of acceleration. You want to be accelerating for as long as possible and then keep that maximum velocity. You don't want to max out the velocity in the beginning, because then you'll just end up kind of slowing down. Not decelerating, but you'd have a negative acceleration when you are moving in the positive direction. You're slowing. Okay? Okay, and I have a couple of links on here if you want to see that. It's pretty cool to watch him run because, yeah, he's just darn fast. But anyhow, I can't show those because they are copyrighted, and last time I tried to put too much copyrighted video into my educational videos, they were blocked. So even though they're for educational purposes, I don't want to get this blocked. So we got these links. You can certainly watch them. They're fun. Okay, so we take a moment to summarize different concepts in motion. So position is talking about where you are at any particular point. That's going to be in meters. So you ask yourself where you are. In velocity, that's going to be meters per second. That's how fast you're going or how fast you're changing your position. Remember, delta V over delta T. And then acceleration is going to be meters per second squared. Those are the units there, meters per second squared. And that's delta V over delta T, right? So velocity was delta D over delta T, displacement over time. I think I said that earlier. Anyhow, yeah, let me just write it in. Delta X or delta D equals D final minus D initial. Anyhow, and I might have messed up earlier when I said this, but anyhow, this is velocity is delta X or delta D divided by time. Velocity equals displacement divided by time. And then we have acceleration is delta V over delta T. So it's important that you see the connections between them, but also see they are their own equations. All right, speaking of equations, let's go ahead and use these equations for physics. We have a car is traveling at 15 meters per second when it experiences a constant acceleration of 3.5 meters per second squared for a time of 11 seconds. What will its velocity be after this acceleration? So whenever we're working these problems, first, of course, we want to read the problem carefully, and then we want to start listing out the information and drawing out a sketch of what's going on. Okay, so here's my sketch of what's going on. Here's a car. The velocity and acceleration are both in the same direction, and then my final velocity, I tried to draw a little bit larger because I know it's going to be traveling faster than my initial velocity. And here's my list of variables. So I list out my givens, and then this question mark is my unknown. And then I say, well, what equation am I going to use? Well, I don't have much in the way of equations just yet. I've got acceleration as delta V over delta T. I've also got the one for solving for displacement and velocity, but we're not really going to use that here. We're talking about acceleration. So acceleration, delta V over delta T, final minus initial velocities divided by delta T. And I can just rearrange that, solving for final velocity, and I plug in my actual values, and I get 53.5 meters per second. Okay, and if you wanted to look at the units, or we can just say 54 meters per second if we'd like, and we can look at how the units did cancel out those seconds squared. And then we move on to where it says a rocket is moving at a velocity of 23 meters per second. It accelerates at a velocity of 85 meters per second over a time of 8.3 seconds. What acceleration did it experience? So once again, we start out by reading the problem, then drawing out a simple little sketch. Our sketches shouldn't have any numbers in it. That's what we have our lists for. In our sketches, we're just saying velocity and acceleration. Pretty soon we'll start incorporating displacement and force and other things. But here we are with our sketch, and here is our list. Okay, in this case, we're given the initial and final velocities, and we can realize that because it says it's moving at this, and then it accelerates to this velocity. You can also look at the units to help you figure out what variable this is. Meters per second, we know is going to be velocity. We just have to figure out, is it initial or final? And it says, hey, what's the acceleration? So that's my question mark. So then I say, well, what's my equation going to be? It's the same equation as we used before, right? Except we don't have to rearrange anything this time. We've already got it rearranged. That's lovely. Go ahead and plug it in. Boop, 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 boop. Meters per second divided by seconds, remember? Anyhow, I got 7.47 meters per second squared. Or if you round it off, that's perfectly fine. 7.5 meters per second squared. Delicious. Delicious. Let's see if we can do another acceleration practice problem. Yes. An object initially at rest. So initially at rest. What does that mean? Experiences an acceleration of 9.8 meters per second squared. How much time will it take to achieve a velocity of 58 meters per second? Okay, so whatever this object is, it starts off at rest, that means the initial velocity is 0. It doesn't specifically say, hey, the initial velocity is 0. With those words, it doesn't have a number in there, but it says initially at rest. Yeah? Okay, fine. So when we go ahead and list out the information, even though it didn't say the words initial velocity, we know that's what it's going to be. Right? Okay. And it says, how much time will it take before it gets to 58 meters per second? So we're solving for the time here. So we use the exact same equation as before, but now we have to rearrange this equation. Solving for t. And because the initial velocity was 0, I just got rid of it. And I got final velocity divided by acceleration. If the initial velocity were not 0, it would be final velocity minus initial velocity, all divided by acceleration. But this is how it is. So now I go ahead and plug in. 5.92 seconds, or if you just had 2 sig figs, it'd be 5.9 seconds. And there's the units working out. The meters over meters cancel. Some of the denominator seconds cancel. It ends up being kind of weird. 1 over seconds. You're like, what? Seconds. Yeah, it's always good to use the units to help you check through your work. It's not going to guarantee your numbers are perfect, but if the units work out wrong, then you know something is wrong, right? Okay. It's good to help us. It's one of several ways to check our work. Okay, and then finally it says, coasting due west on your bicycle at 8 meters per second, you encounter a sandy patch of road 7.2 meters across. Oh, look at this. We're using displacement. That's interesting. You leave the sandy patch, you're now reduced to 6.5 meters per second. So my initial is 8, my final is 6.5 meters per second. Assuming the bicycle slows with a constant acceleration. What was the acceleration? Oh, this is weird. I don't have time here. Now, some people might be tempted to say, oh, we'll just use velocity is displacement divided by time. That's actually not allowed because it's not a constant velocity. So I'm just pointing this out because I want you to see that there is more to learn about this. The equations will become a little bit more complicated. We've learned one equation for acceleration. We've got to learn other equations for acceleration, but not yet. We'll save that for later. Good stuff. Okay, and I also wanted to introduce the motion dot diagram, or sometimes called ticker tape. So let's go ahead and pop this up. And scrolly scroll. So motion dot diagrams. Imagine you are at a party. You got the music playing. Right? You're getting your physics groove on, and you've got your cup of punch. It's delicious punch. It's almost as delicious as physics, of course, but it's not. So anyhow, unfortunately, there's this tiny little hole in your cup of fruit punch, and you don't notice it, but as you are walking across the floor, you are leaving little trails of fruit punch on the floor. Fruit punch is going to be easy to spot, so as you're going, you're seeing little dot here, little dot here, little dot here, and we're going to assume that these drops of fruit punch are coming out at regular intervals. Now, what that regular interval is doesn't itself matter, as in it could be every 1 second, or it could be every half a second, or it could be every 3 seconds. That's not important. The important part is they are at regular time intervals. Okay, so the time between this drop and this drop is going to be the same as the time between this drop and this drop. Okay, so you say, okay, fine, let's just assume that. Okay, because if we can't assume that, it's not going to do us any good. We won't be able to solve anything. Well, then if you take a look at how far apart they are, because this was when my first drop occurred, and then I moved over to here, right? And then from that drop to here, moved over there. That's like the same size arrow, right? And then moved over here. That's also the same size arrow. Same size arrow. Same size arrow, right? We're covering the same amount of distance in each time period. Now, this is drawn out to scale, but the scaling itself doesn't matter as long as the scaling is consistent. In other words, if these are 1 meter, then this would be 1 meter, and this would be 1 meter. Or if they're 10 meters, then they'd each be 10 meters, and so on. The actual numbers themselves don't matter. It's just a visualization of what's going on. My point is, this is telling me that I'm traveling the same distance in the same amount of time, so I must be going at a constant velocity. Constant velocity. Okay? And also because I'm not changing direction and such. Now, what happens if the spacing between the dots is changing? So it says the increasing space between the dots. That means you're going to be going farther during each fixed time interval. So my first time interval, that's how far I've traveled. That's my displacement vector. And then bigger. And then I have a larger still. Even bigger. Woo! Crazy big, right? So in the same amount of time, I'm traveling a larger distance, so I must be going faster. I am increasing speed, or I am speeding up, right? Okay, now what happens if the dots are getting closer together? So look, I'm traveling this huge distance, this way, to the right, and then it's a slightly smaller still, getting notably smaller. So I am slowing down, I'm going slower, or slowing down. Now, what happens if I speed up and I slow down, or I slow down and I speed up? In this case, let's see. I've got a small arrow here, bigger arrow. I'm going faster and faster and faster. Faster, woo, go crazy, yeah. And then what? I'm starting to slow down. My arrows are getting shorter and shorter and shorter. Now, you don't have to draw out these arrows. And actually, some textbooks and some resources and some websites will include the arrows in here, but not all of them. It's not a requirement that they have them in there. Sometimes they use these arrows to indicate, hey, instead of going left to right, like I've been showing on mine, it's actually going right to left. Or you could have them going like up and down. That would also be workable if we're talking about motion in the Y direction. But I think these are a really nice, handy way of helping us visualize things. And honestly, once you start seeing this, you're like, oh, well, yeah, that's pretty obvious. That's a nice representation of what's going on. So nice. Let's actually work through a problem. Yes, motion dot diagram. Sometimes it's referred to as ticker tapes because of a ticker tape lab. Anyhow, imagine something on an object making a mark on the ground at regular time intervals. So it's like your fruit punch is dropping out, right? How would those marks look if the object were A, moving at a constant velocity, B, speeding up, C, slowing down? So you go, let's see, constant velocity, which one is that going to be? Okay, well these distances look to be pretty consistent, right? Okay, so I think that's going to be constant velocity. Yeah. Okay, what about this top one here? Okay, small distance, getting to be larger and larger distances. So I must be going a larger distance in the same amount of time means I'm going to be going faster. I'm speeding up. So that looks like you over here, B. And then let's just take a look here. I'm going big distance, and then slightly smaller distance, and then even smaller. And oh, got those weird extra lines in there. I don't know what's going on. Anyhow, you can see that the distance in between the stars here is decreasing significantly, right? So smaller distance in the same amount of time, I must be slowing. Okay, delicious. And then we've got some of these for you to work through. And then in this case, it's talking, you can actually do various versions of these. In this case, it's a strobe flash is going at regular time intervals, and you see where the ball is at any particular time. In this case, they want you to solve it. Where is the how do they compare for the first first 2 seconds? So, like this is 0 seconds, 1 second, 2 seconds, 0 seconds, 1 second, 2 seconds, 0, 1, 2. You say, oh well, okay. Which one has the largest distance? Which one has the smallest distance? And so on. Okay, but I'm not going to give you the answer here. We'll either go over this in class or I'll give it to you as an ed puzzle or something like that. Ooh, that'd be fun. Ooh. But yeah, we're only looking at the first 2 seconds. I could just as easily have asked for the whole time period or whatever, but that's how this particular question is asked. Okay, and then finally one more of these dot diagrams, these ticker tape things. In this case, you're supposed to draw out the dots for these 4 different scenarios, fun scenarios. You got to read out the names. They're actually rather amusing, but you do have to speak them out until you get the dad jokes built in. Gotta love physics dad jokes. Delicious. Okay, so anyhow, we finished this up. Just making sure we understand that acceleration is change in velocity divided by change in time. So if we're speeding up, slowing down, or changing direction, we're going to be accelerating. The units for acceleration, meters per second squared. When we're talking about positive versus negative acceleration, what's really important is, are we accelerating and moving in the same direction? If we are, we're going to go faster. If we're accelerating and moving in opposite directions, we're going to end up going more slowly. Okay? And then we use some of the equations and solve stuff. That was delicious. And then we also introduced the whole dot diagram business, and we said about the spacings are fixed, and we really just have to look at the distance in between, and then we can see if we are constant velocity or speeding up or slowing down, as in this case here.